Okay. Good afternoon.
Good afternoon.
Here is Thomas Macaulay, Ferguson. He's actually working at Cycorp, and today he's going to talk about the post-consistency of age-connective arithmetic. Professor, thank you very much for being here. You'll have 1 hour for your exposition, and then we'll have 30 minutes for questions from the audience. So you can start.
Okay. So, also, I'm going to set my little stopwatch thing. So, stopwatch there, so I can keep track of how much time I've used. Okay. So, I also have a slight other issue with the slides that a couple of changes I made sort of wouldn't compile. So I'm going to give you last night's version of these slides. But okay, so I want to talk today about something that's very sort of wacky, which is connexive arithmetic. And notably, right, I want to show that the piano axioms closed under Heinrich von Sing's connexive logic is post-consistent. So I also, as part of the icing on the cake, is the simple proof of the post-consistency of the piano axioms modulo David Nelson's logic constructible falsity. And then there's also, I think, a couple of historical points that make that worthwhile. Those historical points that make them into the slide, their way into the slides, but I will tell you all about them. So I plan on giving a little description about how I got to the point that maybe talking about connexive mathematics in general is worthwhile. I want to talk about some of the very negative sort of results that you get when you try and formulate arithmetic in most of the standard, whatever sense you can say a connexive logic is standard. Most of the sort of more well-known connexive logics have some mythologies. I'm going to describe them. And then I'm going to describe doing piano arithmetic in Heinrich von Sing's constructive C. I want to prove its post-consistency, and then I want to talk about some variations on that. So, to give a little background, right, I do think that a very good test for logic, if you have a deductive system, I mean, one of the sort of criteria that's going to have to pass is that you can still do mathematics. So I don't, for any of these systems, I don't really have a lot of hopes that you should do mathematics connexively, that there are things about mathematical truth that really presuppose connexive principles, right? But I do want to say that if a connexive logic is the right logic, then you sure as heck better be able to do mathematics. So having post-consistency of a connexive mathematics is going to be important. That being said, right, I think it's also kind of, there's some peculiarities, especially when I look at the negative results that I arrived at last year, that make it kind of interesting and worthwhile. So strangely, I sort of thought that we could do away with the slide. I assumed by this time I wouldn't have to explain anything about Aristotle's thesis, but here we are. So connexive logics, right, I want to state are any systems that satisfy as theses, right, these two principles. Aristotle's thesis that it is not the case that a formula implies its own negation, and the so-called Boethius's thesis, right, that if a formula implies another formula, then it's not the case that the formula implies the negation of that consequent, right? And these are very plausible theses. I mean, I think in some way they're also completely bonkers when you try and formalize them. But I mean, Nicky Pfeiffer has a paper where he surveys, right, undergraduates about Aristotle's thesis, and you know, people overwhelmingly think that this is true. And Boethius' thesis is interesting because it's made its way into so many things. It's like it's in Ramsey's footnote, right? We get the Ramsey test that's part and parcel of the Ramsey test, right? So these, I think they're salient. It makes them worth looking at. But there's also other formulations, right? You have something called Strawson's thesis that seems sort of an analog of Boethius' thesis. But these are the two things I'm going to sort of target. Right, and of course, connexive logics are notable for being contra-classical, right, insofar as Aristotle's thesis, if you add it to classical logic, you get trivial stuff, everything's true. So you can't add it to an axiom on pain of triviality. But, right, why think about arithmetic in a connexive vein? Well, this does sort of lead to some kind of interesting features. Both, I think, formal and just a little bit more sketchy, but I'm sort of starting to see kind of maybe a ground for something that makes it philosophically interesting for arithmetic as well. Right, so one of the sort of obvious things that make these sort of bonkers trying to do arithmetic in a connexive logic is that decidability is going to be very, very different, right? Right. So if we take something like Robinson arithmetic, right, we know that there are undecidable statements such that Robinson arithmetic doesn't. If Robinson's arithmetic is consistent, right, it doesn't prove either of those things. But given the classical equivalence of one of these undecidable statements, and it's not the case that that implies some negation, right? If you just do this truth functionally, that's equivalent to not G or not G. It's equivalent to not G, and then with the negation on that outside, that's just equivalent to G, if that's a material conditional. So in classical Robinson's arithmetic, should it be consistent, right, you can't prove either of these. But in a connexive arithmetic, well, yeah, you certainly can prove, right, that, right? So that's kind of silly and kind of cheap, but it's also suggests that the landscape, if there were in fact a connexive mathematics, would be very, very different, right? And that strikes me as sort of alluring. I like finding weird things and exploring them, right? So just from that standpoint alone, I think it's already kind of peculiar enough to warrant interest. Yeah. Okay, so that's far from a proof that connexive arithmetic is decidable. But we will, right, as the title of the talk indicated, right, we have decidable theories of arithmetic in connexive logic, right? The more philosophical thing, and this is kind of sketchy, and so, by the way, if at any point I say something bizarre or totally wrong, or you just have an opinion, please interject, shout over me, and I will welcome it. So this is a little more sketchy, but I do think that some of the discussion about Aristotle's thesis before now has sort of suggested that you can interpret connexive theses as sort of a particular philosophy of mathematics or a rejection of a particular philosophy of mathematics, right? So you have this in the Niels development of logic, right, that they sort of point out that, look, you can think about Aristotle's thesis as a sort of rejection of reductio ad absurdum, right? And Neil makes this even sharper, right, that in another paper, that the entailment assertions which Aristotle refuses to admit are just those required for justification of the hypothetical premises in the constructive counterpart of reductio ad absurdum. And so they have a couple of lines that are very suggestive that you could read Aristotle as sort of trying to provide an alternative theory of mathematics. It's not the Zenonian. And that's really suggestive to me. But just a couple of offhand remarks by the Niels aren't really sufficient to sort of warrant investigating, I think. And so I have been trying to think about what to make of this. And I think that you can sort of give some kind of ground, or at least start laying the groundwork for some common principles about mathematical practice that you find with some of the connexive writers. So with Everett Nelson, right, wrote a paper, Intentional Relations. That's sort of one of the canonical connexive logic works, right, where he gave, this is very popular in the 30s, he purported to give an account of true entailment, right, which was connexive, right, nothing implies some negation. And his description of this, right, I quoted it, if P entails P, then P is consistent with Q, right? This assertion, together with the fact that everything entails itself, gives rise to the fact that everything is self-consistent, right? And if you were to accept that P entails not P, then that would entail that there is something that is not self-consistent or is consistent with its own negation, which Nelson finds absurd. In fairness, right, has anybody ever read this paper or knows of Everett Nelson, right? Nelson, right, recanted a year later. I think this was from Mind, and a year later, one of the other few things that Nelson wrote was an admission that, okay, I was crazy in that paper. That's totally wrong. But he certainly believes it at the time, and there is some kind of, I think, there's something that sort of draws me to saying that everything is self-consistent. That's a sort of nice way to rephrase the sort of connexive principles, right? And on Nelson's account, right, this means that there is no proposition, right, such that from its very essence, which is what Nelson takes entailment to be, you can derive its own negation. That would mean that there are propositions that are so sort of corrupt and pathological that they would support their own negations, right? And how this applies to reductiones, right, is, well, I mean, if you just take a very simple reductio proof, like the kind of structure that many of them follows, assume something, and then derive from it its own negation, right? And then this gives us license to reject that principle is false, right? This is the sort of negative counterpart to consequential mirabilis, right? But if you agree with Nelson on this case, then you can't ever do this. There's no way in principle that you can derive some of these negation from its supposition. And if you think you can, then you are using wrong principles, right? And so to follow Nelson on this would be, in some sense, to reject reductio ad absurdum as a legitimate maneuver in doing mathematics or anything. It's just, since reductiones are used so frequently in mathematics, that comes to mind as one of their major applications. And something that sort of strikes me as interesting is another Nelson, and actually in the paper in the connexive logic volume, I cite a further Nelson, right? Edward Nelson. So I had 3 Nelsons in that, but another Nelson, David Nelson, totally unrelated to Everett Nelson, also, right, introduced this logic of constructible falsity, which I love and other people tend to hate. But the basic premise of constructible falsity is tied up with the sort of rejection of reductio ad absurdum as uninformative, right? So with intuitionistic mathematics, right, we, for example, right, require that if we can prove a disjunction, this requires that we are able to isolate the disjunct that's responsible for this truth, right? That's a sort of constructivity of intuitionistic logic and intuitionistic mathematics. And what Nelson sort of points out is there's an asymmetry between intuitionistic proof and intuitionistic disproof, right? And he sort of sees that as being fundamentally dishonest, that the intuitionist says that in order to prove something, you need to do so constructively, but any good intuitionist will tell you that this is totally fine. Phi and not phi is unprovable because it's self-refuting, right? So you ask an intuitionist for a disproof of this, well, they just say, well, look, there you go. It implies absurdity, and therefore we can reject it. But that's not constructive in any meaningful way. It's part of Nelson's whole shtick, right? He says, well, look, I mean, one of the, I think, a very nice case is he gives the case of a negated universal sentence, right? So, in order to refute this for all x, ax, there's sort of 2 paths. One, we can sort of apply a reductio. We can say that, look, suppose that every x is an a. Well, then I can give you some sort of absurdity. I can derive a false one. But in that case, you may not be able to provide some n that witnesses, right, what's actually why one should refute not a. So there's a difference between being able to show that phi implies an absurdity, which is non-constructive and somewhat uninformative, and being able to actually provide a constructive refutation of this. So that's the whole Nelson shtick. And so there's something deficient about constructive disproof, according to Nelson. And right, like I said, a constructive refutation of a conjunction would indicate which conjunct is sort of the refuting agent. What is responsible? What is the cause of, or what is the grounds for the rejection of the conjunction as a whole? Now, what do these have to do together? Well, you have 2 sort of things coming along to reject, or at least diagnose a problem with reductio proofs. Or reductio disproofs, as the case may be. It's not quite clear from just that alone what is common between those, but when you look at Bonsing's connexive logic C, I think that sort of starts suggesting that there is some way to harmonize these things. And one thing that until recently I thought was absolutely bonkers about C, and I acknowledge may still be thought to be bonkers about C, is the fact that you have theorems like this. For any phi, it's not the case that it implies an absurdity, right? Or if you were to look at this intuitionistic style, right? Strong negation, intuitionistic negation phi is a provable theorem of Heinrich's system for any formula. But, right, if I start trying to look at this through my Nelson lens, right, or two Nelson lenses, because I got two Nelsons, right? Double Nelson, one might say. Well, maybe there's a way to give this sort of reading on both Nelson's account. And again, as I said, this is very preliminary. I'm still trying to get my head around this, but it's suggestive to me, right? So what does this mean if you're ever at Nelson? Well, that is really just sort of saying what Nelson is saying, that nothing, we can sort of coherently suppose anything. Everything, any proposition that we can supply is worthy of sort of investigation by trying to conceive of it as if it were true, and then looking at the consequences, right? So from a sort of Everett Nelsonian reading, right, this is just saying that nothing is sort of self-refuting. Nothing is so degenerate as to be able to infer just a straight up bottom constant, right? And following Nelson's reading, you could take this as just saying that there is nothing worthwhile with intuitionist negation, which Nelson's insane. I mean, Nelson says non-constructive negation is good for some things, but it's just not constructive. I'm not entirely satisfied with that, but I think that looking at Bonsing's system actually starts bringing these things into alignment. It's certainly something that's based on a Nelsonian sort of base logic, and it seems to sort of capture whatever Nelson is saying. So I hated C before I came to love it. I'm thinking it's actually kind of cool at this point. But one of the cool things is that we can give post-consistency of it. Okay, I want to try and describe a couple, I'm not going to prove them, but I want to describe a couple of sort of pathological features of doing arithmetic connexively. So the story behind this, right, is that when I was trying to do my PhD, Graham Priest had told me that I should just pick something that nobody ever would try and do, and then give it a good justification, and then everything would be easy street from then on out. But as I was telling Elliot earlier, right, the whole statement, pick something crazy and then make it work, is good as far as it goes, but a lot of things are crazy for very good reasons, right? And so I spent a long time going down all these paths of trying to do connexive mathematics, and yes, there's just a reason why nobody's done it. And I had a handful at some point with just negative results, but at least shows how sort of perilous this thing can be, right? So one of the more, again, you can attenuate this term, famous connexive logics, right, is due to Brad Angel, is this PA1, right? And the way that he gets all of the things is by giving the sort of four-valued semantics. And so you have essentially 0 and 1 sort of operating as truth, and 2 and 3 sort of operating as falsity. But then they also encode this really weird thing where, if you think of that of 0 and 1 as sort of the parity, right, of truth, that conjunctions that agree with one another on parity have parity 1, and things that disagree with one another have parity 0, and you have this sort of mirror image of parity for falsity as well in there, which leads to some very, very weird things. So it gets you modus ponens, it gets you Aristotle's thesis and Boethius' thesis, and in those ways, PA1 is a success, but it also, if you try and really do anything with it, you uncover the pathologies. I'm gonna leave out PA2. Another system which I think is better is Graham Priest's system, which he's never named. The only name for it is that I've given is Pn, right, which is sort of non-symmetrized logic. And the semantics for this is relatively easy, right? You just take an S5 model essentially with a distinguished point. And all of your truth conditions are sort of standard. You've seen these all before if you've ever touched modal logic, except for the conditional, right? And so on pre-connexive logic, what does it mean for a conditional to be true? Well, it means that it's possible, on the one hand, that the antecedent is satisfiable, right? You have to be able to find some possible world in which that antecedent is true. And also, then you have to have the center conditions that in any possible world, right, if A is true, then it follows that B, right? Which gets you connexivity, because the only propositions in classical logic that actually, in fact, logically entail their own negations are contradictions, right? So what this does effectively is it filters out all the bad cases. It says, well, look, well, we had this earlier, right, where we have contradictions don't really entail anything, right? And the same sort of principle applies in this case, right? And then we mirror that in the definition of validity. So we have a non-Tarskian, non-monotonic consequence relation that demands that for the hypotheses, we be able to provide a model that satisfies all the hypotheses. And then on the second, right, barrel of that, right, also say that any such model. So there has to exist a model of the premises, and in any such model, right, the conclusion must follow. Okay, so why do we have these, what are the pathologies in these two cases? Well, I'm thinking about arithmetic. You could think about sets or classes, I guess. I'm thinking about arithmetic, where I have a constant zero, successor function, binary relation, the propositional connectives, and some kind of quantifier in there. So that's the sort of language I'm going to be supposing. I'm also following the Meyer convention of talking about an arithmetic by putting a sharp at there. So if you see a sharp with some kind of deductive system, that just means the evaluation of the piano axioms modulo that deductive system. So that's the language. What are the pathologies? Oh, well, okay. But before I tell you about the pathologies, I want to say that really, I'm not going to go into this in detail, but these were presented as propositional deductive calculi, right? Arithmetic is not a propositional language. So I'm not going to prove it, but anything I'm going to have to say applies to really any natural first order extension of these systems that respects the propositional connectives. Now, here we go. So one of the ways that this sort of weird parity switching in PA1 presents itself is in a very crucial thing that we use in arithmetic of bounded quantification, right? So bounded quantifiers, right? All x less than n, phi x is just a finite conjunction, right? Where we replace each instance of x with 0, and successor of 0, and then, you know, n in that case. Right? And of course, if we have this very, very strange conjunction going on, it will lift to the case of bounded quantification then. And one of the sort of pathologies I can give you is this, right? That even bounded quantifiers where n is even behave very, very, very differently than bounded quantifiers where n is odd, right? So, for example, there are a number of formulas such that say all x less than n plus 2 phi holds, that you can infer that for all x less than n phi holds. But you can't do that for all x less than n plus 1. So I'm not going to go into the details, but can we agree that this is kind of nuts? Right. So I mean, what this is to say, right? I mean, the propositional case is that if I have phi, these are all different beasts. These kind of align, and these align. Finite conjunctions are very, very different than, I'm sorry, even conjunctions are very, very different than odd conjunctions. And I think it's especially, you can look at this and just say, well, that's just a wonky feature of the propositional logic. I will just say never to use these things, but they're super essential in doing arithmetic.
Sorry.
Yeah.
So why even and odd? So that's for every natural number, or maybe you want to have like 2 times n rather than n plus 2?
Oh, okay. So it's the difference between the two. So even, so if I have n,
Yes.
n plus 2 or n plus 4 or n plus 8 or n
It's a
plus
different
yeah.
order.
So any even, I mean, sorry, well, if they agree with respect to parity, so that probably would have been a better way.
Yeah, okay.
If they agree with respect to the parity,
Yes.
or whatever the appropriate word for even and odd is, it's not parity. I always mix up that word. But yeah, so, but that's, I think, catastrophic. I mean, if you actually go get a book on doing piano arithmetic, like Roman cosecks, which is very good, you should all get it. I love Roman cosec. But those things are crucial, right? They're critical. So you really would not be able to do a whole bunch of really important arithmetic without panic quantifiers. Now, with pre-thing, it's really cool and really, really bonkers as well. So this isn't going to hold for something necessarily like Robinson arithmetic where we don't have induction. But it's going to hold for any extension of Robinson arithmetic. If we have, like recursive induction or things like that, anything that sort of gives you an induction axiom is going to be very, 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 very bizarre, right? So I'm just going to say any theory, I'm going to call it a theory that has induction axiom schema in there as, I'm going to call them numerically inductive theories, right? And what I'm going to say is that there are no, in pre-system, in any first order extension that's reasonable, there are no theories in a very sort of, very pronounced way. So why is this? Well, you look at the truth conditions, right, in a PN model as I described it, and take the formula 0 is equal to 0 implies that 0 is not equal to 0. Well, this is unsatisfiable, right, in any model. So let that be our phi, right? Phi of x is that x equals x implies it's not the case that x equals x. So there's no model in which that holds. Now, given our conjunction truth conditions, that means that for this phi, for any c whatsoever, I can conjoin it, and that too will be unsatisfiable. If a conjunct is unsatisfiable, then any conjunction from which it's that is composed by it, right, is likewise unsatisfiable. So any c whatsoever, phi 0 and c has no models, and that means that for any zeta whatsoever, anything of this form, phi 0 and c implies zeta, that this is going to be unsatisfiable. And what is it that's of that form? Induction, right? You can't have anything if you have induction over even, I mean, that's like delta 0, right? 0 equals 0 implies, it's not the case 0 equals 0. So any form of induction worth having, right, is not satisfiable. And given this sort of weird consequence relation, that means that there are no theories that involve this at all. Right, so suppose it's a numerically inductive theory, then that's a member of the theory. This entails a model of that. We can't have that. Now, what's kind of cool, did I add this slide? Yes. What does that mean? Is that arithmetic, piano arithmetic, is decidable in connexive logic, according to Graham's formulation, right? Mm-hmm. Take any arithmetical sentence. Is it provable in P? Your decision procedure? No, right? So it's decidable. Actually, when this paper was refereed, I had a referee comment that said, I can't actually tell if he's being serious or not. But if he is being serious, tell him to remove it. But I was, it's teasing, right? I mean, that's not a benefit. That's not like I've given you decidable. Right, it's degenerate, it's great, right? There are no, right, PA theories, right? Okay, all right, so, now I want to give you something that is more well-behaved. One might reasonably say it's pathological, but I think that pathologies are much, much less severe. And that's Heinrich-von-Sing's constructive connexive logic C. It's based on, as I said, Nelson type logic. And so it is probably important for me to describe Nelson's logic itself beforehand. So N4, right, is Nelson's 1957 logic, which is pair-consistent, which is a very sort of early case of a pair-consistent logic. And the axioms, right, just take your favorite axioms for positive intuitionistic logic, and then add to them some axioms governing how this strong negation operation works, right? So not phi is equivalent to phi. You've got De Morgan's laws, and then very crucially, right, is how we evaluate a negated conditional, right? And a negated conditional, according to Nelson, is phi and not c in that case, right? And why is that? It's because Nelson, when he gives sort of like arithmetical semantics for systems like this, he demands that a refutation of a conditional sentence is a pair, right? It's very sort of BHK in style, is a pair consisting of a proof of the antecedent and a refutation of the consequent, which I think is totally reasonable. It leads to some things like non-substitutive logical equivalence, but, right, it is, I think it makes some sense, right? Yeah. So how do you get C out of this? And also, there's also a quantification one, right? So De Morgan's for quantifiers as well. How do you get C? Well, you just change essentially what it means to falsify a conditional, right? That what a negated conditional is essentially the conditional involving that antecedent and the negation of the consequent. Right? So all you're essentially doing, right, is changing what the refutation conditions for a conditional are. And how does this get us things like Aristotle's thesis? Well, we got, because phi implies phi implies not phi, and then by this interpretation of negated conditionals, it's not the case that phi implies not. Right? It's just an immediate consequence of things being things implying themselves. Okay. So that's how C stands in relation to N4. Now, it's connexive. You can prove Aristotle's thesis, as you saw right there. You can prove Boethius' thesis. Now, one of the things which make me think it's reasonable to say that C is bonkers outright is that it is in fact negation inconsistent. All right, yeah, so what does that mean? Well, phi and not phi does in fact entail, that's not the case in phi and not phi. So a contradiction entails its own negation, but then as a substitution instance of, there should have been a negation symbol there, sorry. As a substitution instance of Aristotle's thesis, right, it's also not the case that a contradiction entails its own negation. So you have, at ground, you have inconsistent theorems, which is very, very unusual. I mean, even in the most hardcore pair-consistent logician typically won't say that this is reasonable. But I think actually you can probably say that maybe it is reasonable, because I'm trying to do that. I'm trying to pick an underdog and make it better. But in thinking about it from the sort of Nelson perspective, I think that maybe you could say that there's a good reason for this. Because if we think about this as a sort of, as a successor to David Nelson, and we think about this in terms of evidence for something and evidence against, well, I mean, maybe we do have evidence for contradiction implying its own negation, and we also have, overwhelming evidence against it. And these things might be in tension, but they would still be reflected in the base logic as an inconsistency. So, what's my evidence for saying that a contradiction entails its own negation? Well, I can prove it, right? By simplification, it implies one of the conjuncts. By disjunctive weakening or addition, it implies its own negation, or it implies, right, the disjoined with not phi. And then by De Morgan's laws and a little double negation wizardry, right, you get not phi and not phi. Not phi and not phi, right? Parentheses don't really work in interlinguists, do they? Okay. So I think that that is a really, really good justification for the theorem of contradictions and failings of negation. What might we say, however, for evidence against it? Well, this is a little bit sketchy, but I think it's kind of reasonable. If you think about sort of like a Lindenbaum algebra or something, you think about propositions as being formulas equated up to logical equivalence, right? Then there's, as I said earlier, there's only one thing that entails its own negation. There's only one proposition that entails its own negation. There are infinitely many that do not logically entail their own negations, right? And importantly, and this is why I think that connexive logic has survived and pops up in so many places, importantly, almost every proposition expressed by one of my utterances in my entire life does not entail its own negation, right? I mean, this cup has water in it. It's not provable in any fair system that should this water or this cup have water in it, then this cup would not have water in it, right? It's not true of, you know, cabbages and kings and sealing wax, all of the things that we actually encounter. None of those things logically entail their own negations. But if we look at that, infinitely many things do not logically entail their own negations. One thing does, well, then it, you know, things don't entail their own negations with probability 1. And so I think that maybe, if you want to be a bit of a smart aleck, you could say that that's overwhelming justification for rejecting as a theorem that things imply their own negations. So it does strike me as some kind of justification for that. And so you could say that, look, I have evidence for a contradiction entailing its own negation. I have evidence against it and express it in the logical language of saying that, look, phi implies not phi in some cases, but in all other cases, in other cases, right, not phi implies not phi. And this seems kind of reasonable to me. But where are we going with it? Okay. How do we do arithmetic? Well, I'm going to try and provide some of these things sort of model theoretically, and I'm not going to try and weigh you down with details, but right, typical semantics for N4 or for C involve essentially Kripke semantics, in which we have two sort of turnstiles here. We have a verification relation and a falsification relation, right? And we just sort of extend these up both simultaneously, right? So you got a collection of worlds, you got a binary relation. It's sort of intuitionistic, it's constructive, right? It's reflexive, it's transitive. And we also, right, treat these worlds as sort of first-degree entailment models, right? Where we have extensions and anti-extensions, right? So at a possible world, right? You know, there might be worlds in which A is not in the extension or the anti-extension of a predicate because we don't have evidence for it. We're going to have worlds in which it's an extension of P, right? Worlds in which we have evidence for it being a P, right? Worlds in which it's an anti-extension of P because we have like a refutation of it. And then, you know, worlds in which we have both a justification and an anti-justification, right? In which, right, a constant or a object is going to be in both the extension and anti-extension. So it's sort of a first-degree entailment-y kind of thing. We expect heredity in both cases. Right, that you preserve these things on both justification and falsification. If I have a justification for a formula, then that will continue to hold throughout my investigation. If I have a refutation, that will continue to hold throughout my investigation. So these things are sort of permanent, heredity holds. And also, right, we're going to assume, just for the sake of making things easier, that everything has a constant and all constants have a referent. Sometimes things may have more than one constants that refer to them. That's not necessary, but it's going to make our lives easier right now. And again, not sort of forcing conditions for these things. But the only thing that really matters, all of these things are intuitionist, right? Or at least very reasonable. All the positive ones, same thing you'd see if you're studying intuitionistic logic on Kripke semantics. We have then, however, just we equate a negation of something as being right, what does it mean to justify a negation? Well, that means that you falsified it. What does it mean to falsify a negation? This means that you've given a proof or evidence for it, right? So you have, again, this sort of strong sort of duality in there. And then we have in, oh shoot, don't look. There. I gave you the Nelson condition. What is a falsification condition in C for, what does it mean for a negated conditional to be true at a world? Well, because we have, right, this, when do I have a sort of refutation for a conditional? Well, that's when I have a justification of the fact that phi implies negation of C, right? So the truth condition just reflects that sort of connexive axiom that governs the negation of a conditional. I'm sorry, I'm terribly sorry that I got that typo there. Does it make sense though? What is a false conditional? It's a conditional that all possible worlds, if the antecedent is true, then the negation of the consequent is true. Okay, so let's actually try and look at these things arithmetically, right? One of the things that when my last paper on this, I ended up with a conjecture about C-sharp arithmetic in C that was motivated by the fact that you can embed C into intuitionistic logic, right? So given such an embedding, it seemed plausible to me that, look, if hiding arithmetic is consistent, either negation consistent or post-consistent, because those are the same, if you're doing intuitionistic logic, if hiding arithmetic is consistent, then C-sharp will be post-consistent. So it was a relative sort of consistency conjecture. But, right, actually we can just prove that it's post-consistent. So, in particular, if you take the piano axioms and you close them under inference in C, right, you cannot prove 0 equals 1. And, right, of course, given, it shouldn't be surprising to anybody that has looked at these sorts of proofs of post-consistency in pair-consistent settings before, we can do so by finite system. What's a general strategy? So, as I said, right, things like this have been done in the sort of pair-consistent tradition pretty frequently, and like we have, proofs of the post-consistency of relevant arithmetic. I'm sorry. Oh heavens! Post-consistency, right, just means that the theory of something isn't trivial, right? That there's something that's not provable, right? You may be able to prove inconsistencies, but you can't prove everything. So that's post-consistency, right? Negation inconsistencies that you can prove some negation. Right, in the classical case, these coincide. If you can prove a contradiction, then you can prove everything. If you can prove everything, then clearly you can prove a contradiction. In the relevant case, though, they don't coincide, right? And the strategy in relevant arithmetic for doing this, and there's a very sort of messy sort of heritage here. So if I'm attributing something to Meyer Mortensen, and I should have attributed to Dunn or something, somebody correct me. But as far as I know, the first real proof that relevant arithmetic is post-consistent, right, involved taking finite models, right, where we take Rm3, which is a 3-valued extension of relevant logic, and we give you, right, a simple finite model of something like 0, and then 1, and then 2, and then back to 0, right, like the integers mod n. And so in such a model, right, maybe the successor of 2 is equal to 0, right? And maybe the successor of the successor of the successor, that of 2 is equal to 2 itself. So we have wonky things, right? And maybe 0 isn't equal to 0, right? But we can't prove that 0 is equal to 1. This does not follow in the model. So we have these sort of finite models in this case that you can prove a lot of wacky things in each of these models, but what they show is that there's a model of something and it's an extension of R and it can't prove some formula, and that means that you can't prove it in R itself. And one thing that I'm going to be relying on a little bit is Priest's sort of discussions about finite class models of arithmetic, right? And Priest has this collapsing lemma, right? That if we take a classical model and we find a congruence relation on it, right? An equivalence relation that preserves the behavior of functions, And then we take the quotient of that model, modulo that congruence relation. Then we have a preservation theorem. We have if phi is a classical consequence in that model, then in this model, which may now be an LP model, a pair-consistent model, or an inconsistent model, phi will remain true in the sort of collapsed structure. Now, although this is frequently talked about as a method of building inconsistent models from classical ones, it actually doesn't suppose that. You can take an inconsistent model, take one of these congruence relations, and continue to collapse it, right? So you can create LP models from other LP models as well. So let's take one of these things where we have, we fix some m and n, right? N greater to or equal to 1 and m just any natural number. And let's say that j and k are equivalent if they're below m and they're actually identified, or if they're equivalent mod n, if they're both higher than m or equal to m, right? And so if we take that sort of equivalence relation, that's a congruence relation, and we can take the quotient of the natural numbers, and we come up with a finite model of arithmetic that is inconsistent, but not necessarily, there's some things that are not true. Okay, and how do we identify literals? Well, all of these things are essentially equivalence classes. So what does it mean for an identity to be true? And in arithmetic, right, the only relation we have is identity. Right, what does it mean for identity to hold? Well, that there are some elements of those such that they are true in the natural numbers. What does it mean for an identity to be false in one of these models? Well, that there is some member of one of these there are members of these equivalence classes that are not equal to each other in the natural numbers, right? So in this case, right, in my little mod 3 model here, y is 0 not equal to 0, because in 0's equivalence class, I also have 3 in there, right? And so there's something in here, 0, that's not equal to another thing in there, 3. So it's not equal to itself. But why is it equal to itself? Well, because 0 is in here, and also 0 is in there, and 0 is equal to 0 in natural numbers. So identity is just that there exist members of these equivalence classes that are actually authentically identical, and a failure of identity is when there are members of those equivalence classes that are not identical. Okay, and the preserve operations. So this is the kind of model that we get from, for example, when m is equal to 4 and n is 6, right? Some observations about a model like this, right? Anything that falls into this loop of natural numbers, mod 6, right, is not identical to itself, right? That's because 10 is a member of this, as is 4, and 16, and 22, right? And so there are elements of this equivalence class that are not identical to other elements. So it's going to make true not 4 is equal to 4. For all JK up in there, if they are in fact identical, then they're equivalent mod 6. For all distinct numbers less than 4, 0, the only member of the equivalence class 0 is 0 itself. These things are singletons, right? And therefore, they are never going to be evaluated as not self-identical. Okay, so boom, by the collapsing lemma, this model right there is a model of arithmetic in LP. And it's post-consistent, right? Does it make true 0 is equal to 1? Well, the only member of 0 that's in there, or the only member of this equivalence class is 0, the only member of this equivalence class is 1, and they're not identical. So it does not actually prove that 0 is equal to 1, and that proves that if you take arithmetic and evaluate it modulo LP, that theory, LP sharp, is post-consistent. Not necessarily interestingly so, but it's post-consistent. Okay. So how can we leverage this in the case of C? Well, take a Kripke model, very simple one. Just take as its model for some fixed mn, the model that we just defined. Have the accessibility relation just be looping to itself, that's transitive and reflexive. And then let's take for the base evaluations that for any identity statement, it's true, there's positive evidence for it, it's verified, if that literal is true in the model, and it's falsified right? If that model itself, the LP model, makes true its negation. So we can easily, this satisfies all the criteria for something's being a C model that I outlined before. So that it is a model for C is sort of trivial. Is it a model for C#? Well, and in most of the cases, we get those things for free, right? We get it for free because in all of these cases, for the extensional stuff, all the truths or the sort of piano axioms for extensional stuff, we just inherit that straight up from Priest's result. Since all of these things are true in the LP model and none of them appeals to any other possible worlds because there are no instances of the intentional conditional in there, well, then we get those for free by the fact that our middle world, our world there, our LP model makes true all of the extensional stuff in arithmetic. So there are two cases that we really need to worry about though, the intentional cases in order to prove this is a model of arithmetic, and those are successor, right, and induction. So we can prove these things model theoretically. Right, so successor, right? Well, I'm not gonna weigh you down with the details, right? But it's really pretty simple. If I do know that there are two equivalence classes in there, J prime and K prime, right? I want to prove that J is equal to K, right? I can just pull out two members of these equivalence classes. I can look at their predecessors, right? And then I can show that these things are going to fall into equivalence class as well. And so successor is almost true, right? And so what that means is that I interpret conditional as the sort of intentional conditional at every possible world, but namely this, because this singleton model, at which the successors of J and K are identical, well, then in that possible world, right, their predecessors are identical as well.
Yeah, can you just give us a little bit more depth on this, particularly in the case where we are looking at like the very first point in the loop, so.
Oh, okay, so, yeah, so if we're doing it modulo this sort of curling structure, that follows just trivially by the fact that in this model, J and K are gonna be singletons. And if they're successors, they're non-zero. And then you look at their contents, each of those is a natural number, single natural number, and then those have to have a predecessor because they're non-zero. And then those things too are going to form equivalence classes. Singleton equivalence classes.
Oh, but we're in the case where we're in the loop.
Oh, when we're in the loop,
But we're,
yeah. So look, I mean, if I'm in the loop, it's gonna work to do this. If I'm in the loop, well, let's just go. Let's do 4, 5, 6, 7, right? So I want to say that 5 is equal to 5, 6, 7, 8, 9.
can we look at 4 being equal to 8?
Okay, 4 equals to 8. Yeah. 5 minutes. Okay. 4.
Or feel free to skip it and just.
Okay. Well, since these things are in the loop, there's something that comes before them, right? So I know that 7 is a member of that, right? And I know that 7 is a member of that. I know that there's some element in here, such that for some element in here, this is the successor of this. I know there's some element in here, such that there's some element in this class, such that the successor of this is in there. And so then it just goes straight down, right? So yeah, I think it's relatively trivial, and then also by the finitude of this, right? Induction falls pretty easy, right? If he holds of 0, and right by my conditional every x, if he is true of x and holds true of successor, then I can just crawl through my finite model. If every possible world, if he is true of n, well, it's just this one. Well, then just go to successor. It must be true of that. Since this isn't like an LP conditional, right? It literally means that the next thing over, if he holds of that as well. And eventually, after n plus n many turns, I've exhausted everything, and I conclude that all x be x, because those are sort of non-LP-ish sort of evaluations. So that gives me all the extensional piano axioms, it gives me the intentional ones, and this is the model of C#. Okay, so Yeah, all right, so it's post-consistent, not relative to HA, but demonstrably and finite statistically. So I'm gonna have to probably eschew the thing. Okay, one thing I wanted to say then is that all of those arguments I just gave hold equally well for Nelson's logic as well. Because there were no points in which here I had to talk about induction when phi is negated conditional, but nothing really rested on it. So no matter what my falsification conditions for a conditional are, this holds as well. So for N4 or for any Heinrich has these other IJ, CK systems, the same thing holds for that as well. And so you get out of this post-consistency for N4 sharp as well, out of this. That's kind of cool from a historical perspective, because in Nelson's 1957 paper, where he introduced this N4 system, he did in the last section, he gave this argument that, well, look, you can have finite models of arithmetic, but he proved it by these very, very difficult sort of claimy realizability semantics, right? Whereas here we just have a very sort of simple model that proves it. So I think it sort of improves on that Nelson's proof in just sort of its elegance. You don't have to worry about arithmetical realizability and anti-realizability, but you just type model. Another thing is that one of the quotes that I had in my sort of fixed up slides, which I don't have, is he said, well, what is this good for? And he said, well, maybe there are mathematicians that haven't made up their minds yet as to whether there are a finite number of natural numbers or not. Well, but it's very easy once you have these sort of Kripke semantics to just apply Woosh's theorem, right? Because you have ultra products on Kripke models really easily, and just provide infinite models. So you can have an N4 or in C, for those models of arithmetic, you can have infinite models. You're not just restricted to finite models. So that sort of satisfies one of the things that Nelson had hoped after. And there are more interesting models that we can build. But we can build cool models like this. We take just those priest models, and then we can build sort of infinite sort of structures. And so the last thing I wanted to sort of say was that I think that given the variety of these models, one of the sort of detriments about the LP and finite models is that they're kind of uninteresting at some point. But you have a lot of room for structure with the Kripke semantics for C sharp and for N4 sharp. And looking at what the properties of those models are, I think is probably, just from a sort of semantic model theorist perspective, kind of interesting to look at. Okay, well, I've run out of my time, clearly. So I'm going to say thank you very much for showing up.
Right. Do you have any questions? Yes. Yes.
Could you use this identity notion in order to produce self-reference in this stuff?
A reference.
Self-reference.
Self-reference.
We usually use identity to produce self-reference in arithmetic, classical arithmetic. So I am wondering if you could use that in order to have self-reference sentences in this stuff.
All right, so one of the things, right? Well, look, so if you, this is from other work I have, but I mean, if you take, for these LP models, for example, so the problem is when you have finite models, right? And you have, right, like a Gödel sentence or something self-referential in that sense, right? It's not clear that it means anything anymore. And there's a problem with just LP in general, right? That if you don't have a conditional, what does it mean to say that I have a proof of this, the Gödel number of this formula? When you have that kind of weird, weak conditional, it's not clear what that means at all. I think so in C sharp and N4 sharp's favor, you do have a sort of more robust conditional, which makes some sense. Maybe saying I have a proof in that case has a little bit more weight. So self-reference, I think, might have some more weight. In these cases, you do escape having finite models, though. So there is, I think, a way that maybe self-reference works perfectly fine. In the sense that if I have, right, like Bev, and then I've got M and N, if I can talk about M and N, those are finite natural numbers. And therefore, if I have a Gödel encoding, I don't know how you're going to do it in C sharp, but it seems reasonable that you would, that these things actually do decompose into proofs. And this does decompose into a formula. you have this problem in general when you start talking about non-standard models, that you have non-standard proofs that don't make any sense. So you're going to have non-standard proofs that are kind of wonky, but I don't think it's going to be peculiar to this case, because you have that in piano arithmetic as well, possibly. But yeah, I think there's certainly a much better hope for something like sort of Gödelian self-reference to hold in one of these arithmetics than you would have in LP arithmetic or many of the sort of other pair-consistent ones. Does that answer your question?
Yeah, pretty good.
Thanks.
Yes, there's question first.
Could I have a finger on this?
Okay.
It's just,
Yeah. Mhm.
so I didn't understand why it's, so in finite models, I understand why self-reference might not make much sense, but I don't understand why it doesn't make much sense in LP models.
Oh, well, in a finite LP model,
Oh, right, okay.
yeah. I mean, look, if you take,
Finite
if you have omega and then you've got, what is it, eta times data out here, right? And you just collapse all of this stuff,
Yeah.
and you've got like omega plus 1. So yeah, so on that count, in terms of do numbers, can you actually decompose them into proofs and formula? Yeah, in the finite case, right, it's very clear that, look, I've said m, but I don't know what number I'm really pointing to, and therefore I don't know what proof I'm really pointing to, what formula. But I think that also just in the case that I have a detachable conditional in Nelson style stuff, that means a whole lot, right? That means that when I say, like, is this, there exists a thing such as has this property, and if it has this property, then that if really means if to some degree. Even if not if means something wacky.
Thanks.
Thanks.
We have another question.
Yeah, so I wanted to push you a bit on just sort of motivationally thinking about this constructiveness to it, or maybe not push you, but just like see how this fits, right? So think about normal Kripke models for intuitionistic logic. Now restrict yourself to one world Kripke models. Lo and behold, it's classical logic. Similarly, think about the models you've spelled out. Now restrict them to one world models. Well, it's this interesting extension of FDE with this, four-valued conditional that's very straightforward and that validates Peirce's law, and it looks like a non-constructed analog of what's going on. And you've shown that thing to be non-trivial too, because your crucial model is a one-world model. So you've shown non-triviality for this stronger system that's adds Peirce's law, adds non-constructive things onto this.
You just seem for this.
So, but I mean, why are we? I see why D. Nelson is interested in this sort of constructive reasoning, but the sort of E. Nelson connexive kind of starting point of, hey, well, things are really self-compatible, even if they're incompatible with other things. Nothing seems sort of constructively flavored about that. So I wonder, like, given that you've got the technology to be showing stronger results than the ones you have in fact shown stronger results than the ones you've told us about, like, what's all this constructive stuff doing? Why is this intuitionistic?
Well, all right. So,
like, you had the full classical era fragment, right? You did non-classical negation, of course, but
yeah, in that case, yeah.
Right.
Well, you'll get the whole intuition. Yeah, I mean, it'll ultimately, if you add more points, we'll get into it. It's positive intuitionistic logic for arrow.
Sure, but why not have positive classical logic, given that you've...
Oh, well, I mean, okay. Yeah, I guess I could have done that. I mean, so von Zing does have this four-value connexive logic, which is its sort of classical limit.
Just the one-world version of this.
Yeah. Which has four-value semantics because it does, right? For those reasons. Yeah, you could have done that. I could do that. We just did it, really. We just did it.
Right, yeah, so why focus on these weaker logics, right? This is, I'm trying to understand something.
All right, because I have, and again, this is very, very weak. Very sort of undeveloped and hazy, but I do have a sense that if you start rejecting reductio, there's a heritage with connexive logic, but it's tied up with sort of rejection of reductiones. You find it in Aristotle, you find it in commentators in Aristotle, you find it with Nelson, you find it with Macaulay. And that seems to be, that bears a mathematical practice, right? That bears a mathematical practice. And you have a tradition that says that constructivity requires that we abandon reductiones. And so there's some kind of harmony there. I don't know that I don't know that this gives
I
them.
think that's a pun, right? I think the connexive rejection of reductio is a rejection even of the kind the intuitionists accept.
Well, no, I mean, but that's Nelson's point, is that the intuitionists shouldn't accept that should not satisfy you if you say that this is refutation. So, I mean, Nelson is rejecting, in probably a weaker sense, all right, so Everett Nelson is rejecting reductiones as possible. Since you can't actually carry out this practice, because if you think that you harbor a thought and you can obtain from that its own negation, then you are mistaken. You are engaging in some kind of faulty principles. You can't really do this.
But where's
David Nelson is saying, say again?
But Peirce's law, right, doesn't involve negation at all. And, right, so none of this sort of questioning about formulations of reductio casts any aspersions on Peirce's law.
I don't know what the status of Peirce's law and Nelson's stuff is.
It's not there if you start from, because it's.
In Everett Nelson, sorry, see, it's a proliferation of Nelsons.
Okay.
Yeah, I don't know
Okay.
Everett Nelson.
Okay.
In David Nelson, it's not
It's
there.
not there.
Yeah, because it's not, because he insists on constructivity and the sort of anti-constructivity as well, that constructivity holds for proofs and refutations. So yeah, Peirce's law is going to go by the wayside. This doesn't reflect, I don't have any devices in here that say, look, I'm making good on Everett Nelson. But it strikes me that there is some kind of kinship or family relation there between rejecting reductiones on two different ways. And I think the shadow, the specter of a reading of Van C is there that sort of satisfies both of these. I'm not giving it because it's still very sort of ethereal in my head. But I think that if it's going to be done, it's going to be done intentionally. Yeah. So could we give a four-valued? I mean, look. So okay, corollary, right? Corollary, right? L sharp is post-consistent, where L is Van Zing's four-valued thing. So yeah, we can do this. Intentional stuff. I think if we're going to get to the heart of any of that Nelson stuff, it's going to have to be intentional, and these are more flexible levels. Did I totally talk past you?
No, that's helpful. I mean, I'm really just trying to see where you're coming from, and I think this is
Also,
somewhere between the Nelsons.
yeah. Well, also, in that the thing is, I try to give a sort of Edward Nelson justification of Graham's stuff, right? And footnote, like David Nelson thinks, or sorry, Edward Nelson thinks that induction is totally wrong. So maybe if you were Edward Nelson, you'd say that we just connexive arithmetic. Yeah. So there's also one of the things that motivates this is you have to understand. I have kind of Stockholm syndrome at this point. I just tried doing connexive mathematics, and then I was beaten. And then I would try doing a different connexive mathematics, and I was beaten. And eventually, I just sort of, well, okay, I'm in a piece with it. And then I have something that kind of works. I was like, so my enthusiasm for it is also historical. It takes in the contingent features of the last 5 years of my life and makes something of those as well. Yeah. All right.
We have another question here.
Thanks, Thomas. Interesting. Let me get to a slightly bigger picture thing. So at the beginning, you started talking about something about contra-classical logics have a burden to show that you can do mathematics in them, or something like this.
Yeah.
Which I thought was kind of striking, but I realized I didn't know what it meant. So
Propaganda.
Sorry.
I'm a propagandist.
Yeah, but what? No. I'm all for. I sort of. What I don't get is, given a suitable consequence relation, right? As you've been discussing, you can take like piano axioms or whatever mathematical axioms you want and do mathematics. So that can't be what you're talking about when you say a mark of a good contra-classical logic is that you can do mathematics in that way. Then the question is, what are you talking about? Do you mean, given our contra-classical logic, we had better be able to get classical mathematics? And if that's the thing, as we were talking about last night, why not just take classical mathematics? And as you're mathematical theory, why worry about being able to recover it with?
Okay, so I'm not.
It's a big picture question, but.
All right, so if you go to the negative results, it's not just that, look, you can't do all of mathematics. It's you can't do mathematics.
Sorry, but what, I guess I'm asking, what do you mean by mathematics? I mean, do you mean do you mean like classical mathematics? Like our best mathematical theories as practiced by those who take classical logic to underwrite it? So when you say you can't do mathematics, I don't know what you mean.
All right, so I'm going to say that if you have a theorem of reasoning, and your theorem of reasoning as a consequence means that mathematical induction is logically false, there's a problem. I think that it has to, that's why the connexive stuff and contra-classical stuff has an additional sort of burden. Because if you're doing a relevant logic or an intuitionistic logic or a Nelson and Ford stuff, any of these things, you can do that. You're like, well, look, okay, you can't derive this theorem from the Peano axioms and your logic. We'll add it. Yeah, I totally get that. But in contra-classical stuff, because it goes outside, it doesn't just sort of not. So with relevant arithmetic, that was the whole sort of Meyer-Friedman thing, right? Is that you remove the warrant for certain mathematical theorems if you weakened it to relevant logic, right? It's not just removing the warrant, right? It's blocking mathematics. In Priest's case, for example, or in Angel's cases, if you try to do mathematics and you think that this is how logical operators work, you're not able to do mathematics any longer. So if I were to say, look, Angel's logic is right, PA1 is right, it doesn't give me a good, the bounded quantifiers act a little bit wonky in that, but I'll repair that just by putting into my theory theses that make bounded quantifiers work. What I would get was I would get a trivial system.
Is there more of a cue? Because
You're good.
okay.
I hope I'm not going past you.
Well, I may be talking about you, but I actually am very, very interested in your response here. I mean, so am I understanding correctly that when you say, given a contra-classical logic, so talk of the Meyer-Friedman, you've removed, we had something that we took to be true, and when we thought logic was this way, we thought that P was true. Let P be something we thought to be true. When we thought logic was this way. And we had a derivation for P, and maybe that's why we thought it was true. Now we've come to see, no, logic is actually different, it's not that. Now the question is, why think P is true? Why not just reject its truth? And that's mathematics. Or you say, no, P is absolutely true, in which case, why do you need to derive it? If you're so convinced it's true, throw it in there.
Okay, so
that's where I
totally
don't
happy.
think-
Yeah, okay. But this is, again, because we're not just weakening classical logic here. It's not just a matter of I have lost, we never have warrant for AC. We don't have warrant for continuum hypothesis. But I think adding them in there is reasonable if you really believe them, and that's fine. But that's not what's going on. It's not that we, look, it's with Graham's logic. It's not that, look, we had a proof or we had some sort of logical justification that seemed to provide us a reason to think that induction is good. And now we've lost the warrant for it because we say that our logical principles are weaker. Well, why not just put induction back in there? It's actually the logic itself is incompatible with mathematical induction.
So why is that a case? Last
Yeah.
question. Sorry. Why is that a case of not being able to do mathematics?
I don't know. I mean, if you're Edward Nelson, maybe.
No, it's a serious question. I mean,
Yeah.
I just don't get. It just looks to me like a case where you think mathematics is vastly different from what we thought it was, because you can no longer have induction.
Okay, well, yeah. I mean, maybe that's the case.
Okay.
And as I said, I mean, there are people out there. I mean, Edward Nelson would not have been sort of, okay, well, let's be connexivist about stuff. But if anybody would have been satisfied, it would have been him. And maybe in a case like that, you say, well, look, what we've learned is that some of our mathematical principles violate logical norms, and therefore we should throw them to the side. But, I mean, again, it's Zach had this. The first time I ever saw Zach Weber, right, when he was a little baby undergrad, or baby graduate student, right? Right, he had this, striking sort of thing that mathematical truth precedes logical truth. And I don't know if that's entirely true, but it's certainly, I will accept to the point that you better be dang sure that you're preserving mathematical truth. And I think that induction is totally true. And I think that most people do. And I think certainly bounded quantifiers work well. And I think that some of the other, like PA2 has its own set of pathologies. And I think that these just violate my mathematical intuitions to such a great degree that that has to be a problem with the reasoning system, the logical theses, rather than the mathematical practice itself. So it's not a matter of I don't know what I would say, like taking the bathwater and putting the baby back in there after you've rejected in favor of another baby or something like this. I mean, I'm sure there's some permutation of the baby in the bathwater idiom that would work in this case, but I'm not that quick on my feet. But
No, I was just trying to understand the sort of burden that you put forth for a good contra-classical logic, and I think I have a better sense.
yeah. Look at like, I mean, if you're a parity-consistent person, I mean, and you're it's that exchange over the Mortensen and Burgess thing about playing cards, right? Like if you're a relativist, you can't play cards; I will beat you to death in Clue, right? Well, okay. I assume certain reasoning principles when I'm playing Clue, and now I'm not a victim anytime we play board games anymore, right? Because I can use disjunctive syllogism. So I respect them, but in a case like this, it's not just, well, in certain contexts, I can endorse new principles. I can't endorse those principles. Those principles are always false.
Always false, or like
Logically
post
false.
inconsistent resulting.
Posting just trivial,
Okay.
trivial logic.
Okay.
Well, in Priest's case, it's weird because it's not that the theory of piano arithmetic is the language. It's that there is zero consequences. There's nothing. There are no consequences because of this weird sort of validity relation. But yeah, I think that's bad. I think you say there's no mathematics. It's bad. That's just me. I like mathematics.
We have time for one last question.
Yeah, it's just, I didn't understand, so you could have some instances of induction, right?
No, well, okay, yeah, some. But I mean, usually when we talk about different sort of hierarchies of induction, I mean, what is my induction? I mean,
So you don't cuts like this, like in the code of the arithmetic hierarchy.
yeah, so, all right,
Arithmetical hierarchy.
to be honest, not that I was being dishonest before, but look, I mean, maybe you could do in Graham's PN, maybe you could say, like, this is what induction is. Induction is only over extensional contexts. But even then, you can't ever have induction over contradictions. So maybe only positive extensional formulas, then I have induction, but that's really weird. So okay, so maybe that's the lesson that we learn is that, full induction was false, and induction over intensional context is false, and induction over context including negation is false. It's just primitive, positive, extensional formulas, maybe. Maybe you could do it, I don't know. I just got so discouraged I didn't try more.
No, just
But yeah, no, that's
checking.
true. That's true. I gave an instance, but I took it because it's a simple instance. It's not, as I said, it's like delta zero. Like it should be good, but maybe it's intentionality. I mean, if you told me it seems that maybe there is a huge distinction over triggering induction over extensional and intentional contexts. I mean, maybe that is a really good dividing line, and maybe you can revisit this and do it. I don't know. Thanks for keeping me honest. All right, I think that's it. Thank you very much for bearing with me.